I'm Jianting Yang, and I'm a PhD student from University of Chinese Academy of Science. Today I will talk about computing sparse Fourier sum of squares on finite abelian groups in quasi-linear time. It's joint work with Ke Ye and Li Hongzhi. So the basic problem is a generic combinatorial problem, optimization problem. Here we see given a finite set S, where S equals to S0, S1 to Sn minus 1, and the function f from S to real number R. We want to verify that whether f is a non-negative function. We select a finite abelian group G equals to G0, G1, G2 to Gn minus 1, and the bijection from G to S such that phi Gi equals to Si. Then verify that f is a non-negative function is equivalent to give a Fourier sum of squares of the combination of f and phi. So here is an example. We say if let set S equals to be 0, 1, 2, and 3, and the function fs equals to 0 if S is odd, and equals to 2 if S is even. We choose G to be the group C2 to the power of 2, which is a direct product of minus 1 and 1. And the bijection phi is defined as follows. We can verify that f is a non-negative function by give a rank 1 Fourier sum of squares of the combination of f and phi. Here we remark that since x2 belongs to the group C2, then the square of x2 equals to 1. Now, let's recall some basic knowledge of group theory and representation theory. Here, we write Zn to be the cyclic group of order n with modular addition. The fundamental theory of finite abelian group says that if G is a finite abelian group, then G is isomorphic to some direct product of the cyclic group for some integers n1 to nk. And the complex function on finite abelian group G is called the character of G. If it satisfies that chi x y equals to chi x times chi y for any x and y belongs to G. We write G hat to be the set of all characters of G. And G hat is also known as Fourier basis or dual group of G. Since G is a finite abelian group, then we have G hat is also a group which is isomorphic to group G. And for any function from finite abelian group G to complex number C, f has a unique form, which is a linear combination of the all characters of the group G. And the support of f is defined as the characters whose Fourier coefficient is not 0. For example, let's consider G equals to Z6. Then G hat equals to chi 0, chi 1, chi 2 to chi 5. And here, chi 1 equals to be exponential to the power of 2 times I times pi times x divided by 6. And chi k equals to chi 1 to be the power to the power of k. So let's consider about the Fourier sum of squares on finite abelian group. So let G be a finite abelian group, and f is a function from G to complex number C. The theorem from paper of Fossey, Sanderson, and Pavlov in 2016 says that f is a non-negative function on group if and only if it has a Fourier sum of square form, and only if there exists a Hermitian positive semi-definite matrix Q. Q is indexed by G hat, such that f have the following quadratic form. And here we remark here the matrix Q is called a gram matrix of f, function f. And we remark that the gram matrix is not unique. So here is an example. We consider f is a function from Z6 to complex number C, and fx equals to 1 minus 1/2 times chi 1 plus chi 5. A gram matrix of f is shown in this page. So By Cholesky decomposition, we can find that a gram matrix is corresponding to a Fourier sum of squares of a given function. Here, we write the Fourier sum of squares corresponding to the previous gram matrix. Here we can see that this Fourier sum of squares is very dense and involves all of the characters of G hat of group G. We define the sparsity of the Fourier sum of squares as the characters involved in the Fourier sum of squares. For example, the sparsity of this SOS is 6. So, and we know that a sparse gram matrix is corresponding to a sparse Fourier sum of squares. By graph theory, we know that F admits a Fourier sum of squares with sparsity 4. But this function F has a sparser gram matrix, which just consists of characters chi0 and chi1, and it is corresponding to the sparser Fourier sum of squares, whose sparsity is 2. So we wonder how to compute the sparse Fourier sum of squares. Let's say compute the sparse Fourier sum of squares is equivalent to compute the minimal value of L0 norm of the diagonal elements of gram matrix. And we know that L0 norm optimization problem are always hard to solve. So we may consider its convex relaxation problem, which is a L1 norm optimization problem. However, unfortunately, since G is a finite abelian group, the L1 norm of the diagonal elements of gram matrix are always constant. So we must change our problem. By this theorem, we can see that the previous L0 norm optimization problem is equivalent to the right-hand side L0 norm optimization problem, which just removed the chi0 entry of the gram matrix, and chi0 is the map is a function from group G to complex number C, which maps all of the elements to 1. And the right-hand side optimization problem, the convex relaxation of the right-hand side optimization problem is not constant. So we can consider its convex relaxation problem. We can see it's a SDP problem. So we may use SDP solver to solve it. However, the time complexity of the SDP solver is at least the cardinality of group G to the power of 4, which is not a quasi-linear algorithm. So we wonder if there exists a fast method. And here we prove this theorem. Let f be a non-negative function on G, and h be its square root function. Here, that is to say that hx equals to be the square root of fx for any x belongs to group G, and the a chi to be the Fourier coefficient of function h. Let q0 to be the matrix indexed by G hat, and q0 equals to the out product of the Fourier coefficient vector a chi. Then q0 is just the solution of convex relaxation problem. So this theorem gives us a closed form solution of the convex relaxation problem. And of course, we can use FFT and inverse FFT to compute the function hx. So the complexity is quasi-linear of the cardinality of group G. However, the solution of the convex relaxation problem gives us a Fourier sum of squares, but this Fourier sum of squares is dense. So we must do some truncation in order to find a sparse solution. So let's sort the diagonal elements of Q0 in decreasing order. And for each k, integer k, from 1 to the cardinality of G or G hat, we define Sk to be the set of gram matrix of F with support the sparse equals to the k largest diagonal elements of the solution Q0. Then we aim to find the minimal k such that Sk is a non-empty set by bisection. To conclude, the total complexity of our algorithm with input f is at most quasi-linear to the cardinality of group and the polynomial to the output FSOS sparsity. So here we give a running example. Let's say we still consider this function f. And the solution of convex relaxation problem Q0 is the out product of this vector a chi. Here in this page we show the a chi. And we sort the diagonal elements of Q0. So now let's consider about the set Sk. Here, S1 equals to be the gram matrix of f with support just chi0, and it's an empty set. But S2 is a gram matrix of f with support chi0 and chi1. By SDP solver, we can find that S2 is not an empty set, and this matrix belongs to S2, which is shown before, and is corresponding to a FSOS with sparsity 2. And here we also do some numerical experiments. In these numerical experiments, we randomly picked some non-negative functions on a given group with bounded degree, and use our program to compute Fourier sum of squares, sparse Fourier sum of squares, and compare our sparsity with theoretical bounds given by Fuzzy, Sanderson, and Perlow. So firstly, we can find that the the sparsity of output is much sparser than the theoretical bounds, and we can say that we can compute a function on group up to whose cardinality is up to 500 million in half an hour. And in this numerical experiment, we randomly picked some Fourier sums of squares with bounded sparsity, expand them, and use our program to compute it. Firstly, we notice that we can compute the function on group whose cardinality is up to 1 million in half an hour, and we can find that our the output sparsity is not it's stable. Well, when the cardinality of group increased, it doesn't increase. So, and an important application is the certification of max set problem. So let's recall some basic knowledge of max set problem. Here, let x1, x2 to xn be Boolean variables, and the literal is the atomic formula in form of xi or not xi. And the clauses is a disjection of literals. The conjective normal form, in short, CNF, is a conjecture of clauses. For example, here, phi equals to x1 and x2 and x3, and not x1 or not x2 or not x3. The max set problem asks the minimum number of falsified clauses in given CNF formula. For example, we still consider this phi. The minimum number of falsified clauses in phi is equals to 1. So how can we use change the max set problem into a function on a finite abelian group? Let's define Cn2 to be the n times direct product of the group minus consists of whose elements is -1 and 1. And then the Fourier basis of group Cn2 is a square-free monomials in n variables. For example, the Fourier basis of C22 equals to 1, x1, x2, and x1 times x2. We set -1 to be true and 1 to be false. For integer L, we define HL to be the polynomial such that the value of HL equals to 1 if all of the input is 1, and equals to 0 if there exists some input yi equals to -1. And for clause C equals to the disjunction of x1 to xs and not xs to plus 1 to not xs plus r. We define function fc equals to the function hs plus r for y1 to ys and minus ys plus 1 to minus sys plus r. For sinf formula phi, we define the characteristic function of phi to be the sum of the fci. For example, we still consider this phi. The characteristic function of f phi is shown in this page. We remark that the value of f phi for input y equals to be the number of falsified clauses in sinf formula phi with assignment y. And we notice that the character functions are always integer valued. So the number of falsified clauses in sinf formula phi is at least integer L is equivalent to that if there exists a finite family of function G such that the error of f phi minus L plus 1/2 and the sum of the squares of G is less than 1/2. However, if we still use our previous algorithm, then the complexity of ft will be n times 2 to the power of n, and this complexity is not acceptable. So we wonder if we could compute the Fourier sum of squares, the sparse Fourier sum of squares faster. We should faster than the fast Fourier transform. So let's consider if f is a function on finite abelian group G. F is at least 0 and at most m. We define the finite norm of f equals to be the maximum absolute value of function f. If there is a polynomial q such that q approximates the square root function in interval from 0 to m with error less than epsilon, then we consider the composition of q and f. We can see the composition function approximates the square root of f with error less than epsilon. And of course, the square of the composition of q and f and the function error is also bounded. And of course, the error of the Fourier coefficient are also bounded by epsilon. So the combination of q and f gives us a good estimate of the square root function, and it's easy to compute. We remark that the sparsity of f is s implies that the sparsity of f combination function of q and f is at most s to the power of degree q. Let's see an example. If we set f equals to be the f phi minus 1/2, and the q to be the linear function that approximates the square root function at points 1/2, 3 seconds, 3 seconds and 5 seconds with error less than 0.005. Then we can find that the combination of q and f is close to the square root of function f. We can see that the error of Fourier coefficient is at most 0.03. So we wonder, when will we have a low degree polynomial Fourier sum of squares? We proved this theorem here. Let phi be a sinf formula with m clauses, and let f phi be a character function of phi. If f is at least alpha times m for some alpha greater than 1/5, then for any beta greater than 0 and less than 5 times alpha minus 1 divided by 4, there always exists a rank 1 Fourier sum of squares certificate of degree O log m for function f phi minus beta times m with error less than 1/4. We interpret this theorem by this future, and the sinf formula in shadowed region has a low has a low degree rank 1 Fourier sum of squares. So we may ask if the lower bound of alpha can be removed, but we proved this impossibility theorem. Here, let epsilon is greater than 0 and less than 1/2, and p is a polynomial such that p approximates the square root function at the integer point from 0 to m. Then the degree of polynomial p is at least the fourth root of m. So we cannot remove the lower bound of alpha, but we can just improve the lower bound, but we cannot remove it. So we may ask about the rational case. Here we prove that if phi is a thin F formula with m clauses, and f phi is its characteristic function, and f phi is at less L, then there always exists a function g and h such that the rank 1 rational Fourier sum of squares of g and h approximates the f phi minus L plus 1/2 with error less than 1/4. And the degree of g and h equals to O square of log m. So we may compare the polynomial case and the rational case. We can see that the polynomial case, the lower bound is the m to the fourth root of m, and the rational case is the square of log m. Thus, the low degree rational rank 1 Fourier sum of squares always exists. Then we should consider about the verification method. We want to verify the error between f phi minus L plus 1/2 and the rational Fourier sum of squares is less than 1/2. But if we use the naive point-wise verification method, then we must compute the error at all of the points in the group, which is of the size 2 to the power of n. However, we give this theorem. Now, let G and Hi gives a rational Fourier sum of squares, and let D to be the degree of G and Hi. We just need to compute the error of the points with order at most 2D minus n plus 6 to check whether this points, the error of these points is at most n to the power of minus 2 times square of log n. We don't need to compute the 2 to the power of n points. So we can compare the naive method and our sampling method. We can see the left this figure. The left figure is the number of sample points required by these two methods, and the right is the accuracy required by these two methods. We can see that the sampling method requires higher accuracy, but less number of simple points. And another one is that we can verify the error of rational Fourier sum of squares by L1 norm. Suppose that Hi and Gj to be a function from group C2 to the power of n to real number R satisfies that the gram matrix of there exists a gram matrix of the sum of squares of Hi such that the gram matrix is greater than identity matrix, and the L1 norm of the error function is at most 1/4. Then the error between the f phi minus L plus 1/2 and the rational Fourier sum of squares is at most 1/4. So we can find that this condition can be computed by SDP, can be verified by solving a SDP problem. So we also use our algorithm to compute the 3-sigma F formula with n variables and compare our time cost with a max set proof system named MS Builder and MS Checker. We can see that for some example, the proof systems run very fast, but for some example, it takes a lot of time. However, our FSOS program, the time cost of our FSOS program is quite stable, and it doesn't increase while the so we may compute larger problems, and this is our reference. Thank you for your listening.
Thank you very much for this talk. Question. Bernd.
So the set of gram matrices that represent a given function is a spectrahedron, the grams. Has this been studied in this case? So for a given function, what can you say about the spectrahedron of all gram matrices? What's the low ranks you observe there? So you said the gram matrix is not unique. As the set of
yes,
gram,
yes, the gram matrix is not unique. So what's the problem?
The question is, let's look at all gram matrices for a given function f.
Yes.
So that's the spectra. Has this spectrahedron been studied?
No, we haven't studied it. Sorry.
Yes, of course.
So can you move to the table with your numerical examples?
What? A table, a numerical experiment, yes. So
I mean,
this?
Yeah, I didn't quite get how you get these very sparse, like these very sparse sum of squares. What was the procedure in this?
So sorry.
How do you get these sparse SOS?
Just by this algorithm to we compute the minimum k such that Sk as a non-empty, and the elements in Sk is a sparse gram matrix, and we use this gram matrix to compute a sparse Fourier sum of squares.
Okay, that's fine.
Okay, if there are no more questions, let's thank Jianting again for this nice talk from
Thank you.
From remote, and we have time until 11:15.